Hello everybody, it's Tarun. Welcome to your 6th tutorial in the Signal System and Control course. In the last tutorial we learned about the properties of the LTI system. Okay, and now moving forward we'll learn about difference and differential equations and their representation and block diagram representation of systems in this tutorial. Okay, this is last tutorial for unit 2. Okay, after this tutorial I'll provide a assignment to you with hints also, so you should do the assignment by yourself without looking at the hints as least as possible. Okay, so now let's start with the differential and difference equation representation. Okay, it is a powerful tool to represent systems. Okay, the continuous time systems are represented by linear constant coefficient differential equations. Okay, and the discrete time systems which are represented by linear constant coefficient difference equation. Okay, so in general they provide us initial conditions, initial system energy, etc. Okay, so now let's see the linear constant coefficient differential equations. Okay, so they are represented in this manner. Okay, the general standard representation is that for nth order. Okay, this is for output terms and it is for input. Summation k is equal to 0 to n a of k. Then it is differentiation of y of t k times. Okay, and it is equal to summation k is equal to 0 to m bk, and differentiation of x of t k times. Okay, so this you know that differential equations have two solutions. One is homogeneous solution and another is particular solution. So the solution y of t will be represented as the sum of homogeneous solution and the particular solution. So how can we find the homogeneous solution? We take the right hand side, okay, and put it equal to 0. Okay, and for particular solution we take any solution ypt for given x of t. So initial condition, how can we check for x of t is equal to 0 and for t less than t naught, such that y of t for t naught minus, which is t less than t naught, okay, is equal to dy over dt, which is at t naught minus, which will be equal to t2y over dt square at t naught minus, and it will go up to dn minus 1 yt upon dt n minus 1 at t naught minus. Okay, it will be 0 because we are corresponding to causal LTI system. Okay, for causal LTI system this condition must follow. Okay, so now let's see with an example. We are given the first order differential equation, this. Okay, and we have input k e to the power 3t for t greater than 0 and k belongs to R. So for particular solution, okay, let's take phi pt, which is our particular solution, is equal to the input y e to the power 3t. We have replaced k with y. So if I replace the value of phi pt with our equation, okay, then we get y equals to k upon 5, and we get our particular solution k upon 5 e to the power 3t. Okay, now let's see for the homogeneous solution. Okay, we put dy over dt plus 2yt equals to 0, and we consider yh, which is our homogeneous solution, as a e to the power st. So when I put the value of y of h of t in this equation, okay, I get s is equal to minus 2. So it gives a homogeneous solution as a e to the power minus 2t for t greater than 0. So to get the whole solution we need to combine the homogeneous solution and particular solution by adding them. So when I add this homogeneous solution and this particular solution, I get this output, okay, which is for t greater than 0. And for initial rest condition is y of t equal to 0 for t less than 0, because x of t is equal to 0 for t less than 0. Okay, so no impulse is produced at t is equal to 0 implies that y of 0 is equal to 0. So which gives us the equation a plus k upon 5 equals to 0. Okay, so with the help of this equation I can replace a with k minus k upon 5, and our complete solution will look like this. Okay, so now let's see the discrete time case, the linear constant coefficient difference equations. So generally in nth order they are represented in this manner. Okay, where it is summation k is equal to 0 to n ak y of n minus k is equal to summation k is equal to 0 to m bk x of n minus k. So similar to the case of differential equations, it has two solutions inside it, which is one is homogeneous and another is particular solution, and the complete solution is the sum of both. Okay, for homogeneous solution we put the left hand side equal to 0, and for particular solution we take any solution yp of n for any given x of n. Okay, and similar with the continuous time case differential equation properties, the condition of initial rest is that x of n will be 0 for n less than n naught. Okay, then y of n will be 0 for n less than n naught. Okay, alternatively I can rewrite the difference equation as this. Okay, 1 upon a naught sigma k is equal to 0 to m bk x of n minus k minus sigma k is equal to 1 to n ak 1 of y of n minus k. Okay, so now let's see with an example. We have a non-recursive difference equation, okay, which is y of n equals to x of n minus x of n minus 1. So impulse response of the underlying equation can be obtained when x of n equals to delta of n, and then y of n will be h of n. So h of n equals to delta of n minus delta of n minus 1. So since h of n is equal to 0 for n greater than 2, so the underlying system, okay, will be referred as finite impulse response system. So why h of n equals to 0 for n greater than 0? Let's see. If I put n equals to 0 here, so you can see that it will be h of 0 is equals to delta of 0 minus delta of minus 1. So delta of minus 1 will not exist, and h of n 0, delta of 0 will be 1. So h of 0 equals to 1. Now if I put n equals to 1, then h of 1 equals to delta of 1 minus delta of 0. Okay, delta 1 will not exist, as or it will be 0, and h of 1 will be equals to minus delta of 0, okay, which will be 1 minus 1. Okay, now if I put n equals to 2, then it will be h of 2 equals to delta of 2 minus delta of 1, so it will be equals to 0. Okay, and for n equals to 3 it will also become 0. So now you can see that it will be 0 for n greater than or equal to 2. And now if we consider the recursive difference equation, okay, this equation, so I can rewrite it in this form. Okay, so if I check the impulse response of this LTI system, okay, y of 0 equal to x of 0 plus y of minus 1 by 2. So y of minus 1 is not existing because of the condition of initial rest, okay, which is y of n equals to 0 for n less than 0, since x of n equals to 0 for n less than 0. So x of 0 will be 1 because we are finding the impulse response. It means that we are replacing y with h and x with delta. So if I calculate y of 1, then it will give x of 1 plus half y of 0. So x of 1 will be 0 because delta of 1 will be 0, and y of 0 is 1, so you can see that it is 1 by 2. So similarly, when you proceed this operations, you will get y of n equals to 1 upon 2 the whole power n, and you will get the impulse response function as h of n equals to half to the power n un. Since h of n has an infinite duration, the underlying system will be referred to as infinite impulse response system. Okay, so now let's see the last topic in our unit 2, which is block diagrams. It is a representation of systems which is useful for analysis, design and implementation. So there are few basic modules for the block diagrams. One is addition. Okay, you represent the addition in block diagrams like this. You take one input x1, another input x2, make a circle and plus sign inside it, and you need to use arrows that the signal is coming from here and the signal is coming from here, and the summation is going to there, which will be equal to x1n plus x2n. So if I want to multiply any signal with a scalar, then what do? I make a line, put an arrow, and then write the scalar over it. So this is the representation of how to multiply scalar with a signal, and this is the difference. Okay, or delay. It delays the circuit, the signal by one value. Okay, so now let's see this equation. Y of n equals to a y of n minus 1 equals to b x of n, or I can write it as y of n equals to minus a y of n minus 1 plus b x of n. Okay, so how can I design the block diagram of this equation? So I have x of n, I need to multiply it with b. So I have multiplied it with b here, and then I need to sum it with minus a of y of n minus 1. So I have here output y. I take the output and delay it by one value. Okay, then I multiply it with the scalar minus a, and then I sum it with the b x of n, and then I get the desired output y of n. Okay, so this is the representation of block diagram for an difference equation. Okay, so how is it working? That if I am, you remember that the difference equation says that the output, just wait, let me just show you only. Okay, we are making the block diagram for this equation. Okay, so here you can see that I am multiplying x of n with b0, then delaying it and multiplying it with b1, then again delaying it, then with b2, and then so on till m delays, and then multiply with bm. Okay, and then I'm summing it with all these values, summing all these values to get the summation term of the x function, x signal. Okay, and for y, I am initially multiplying it 1 upon a0, then minus a1, then minus a2, and minus an minus 1 up to minus an, and I am delaying it also by one value in each multiplication, and then summing it to get the desired output. Okay, and this is the direct form 2. Okay, this is a homework for you to determine how does it work. Okay, and now let's see. Okay, sorry, this is direct form 2. It is for you to determine how is it functioning, and you can also make this block diagram by interchanging the d's. Okay, by placing this d over here and this d over here. Okay, as you can see that I have done that, and you have to figure out the direct form 2 yourself. This is homework for you. Okay, now let's see for the continuous time case. Okay, for continuous time, the similar function is there for addition and for multiplication with scalar also. Okay, and there is difference between continuous time and discrete time in this basic module, which is integration module. Okay, here I am integrating the signal from minus infinity to t. Okay, so if I have a differential equation in this manner, okay, I can write it in this form also by integrating it. So how do I represent it? I need to multiply x of t with b. Okay, I have done that, and then I need to multiply a minus a with y of t. Okay, I have done that. Then I need to sum both and then pass it through the integrator. Okay, so I have done that. So there is one more thing. Instead of integrators, there are differentiators also, which is represented by d upon dx. instead of integration sign you can write d upon dx, which will differentiate the signal. But it is more practical or convenient to use the integrators instead of differentiators, because the integrators are easier to implement and are more or less sensitive to errors and noise, whereas differentiators are difficult to implement and extremely sensitive to noise and error. Okay, so this is the nth order differential equation for the continuous time case, and I have represented it in the direct form too. Okay, so there is another homework for you, is that you need to make the direct form one of nth order differential equation. Okay, so this was all from my side in this tutorial, and as I told you earlier that I have provided an assignment with this tutorial, so I need you to go to the assignment, do the questions by yourself. Okay, after doing the questions by yourself, you will find these things easier. If you are finding any problems with these direct forms, then you can look up in the book. Okay, they are easy to understand. If you try and do some questions on them, then you will easily grasp the concept of these equations. Okay, so thank you guys for watching. I'll see you in the next tutorial, where we'll start unit 3, which is Fourier series. Okay.